Welcome, everyone. Before we touch a single wire or write a single line of code, we are going to build the mental model that every competent embedded engineer carries with them. The title of this module is Anatomy of a Microcontroller, and the subtitle tells you exactly where we are going. From core hardware theory to industrial integration. Look at the image in the center of this slide. What you are seeing is an ATmega 328P microcontroller chip. Notice the arrows radiating out from every pin. Each one represents a signal, a piece of information, or a voltage that the chip either reads from the world or writes back to it. This one small chip is capable of controlling motors, reading temperature sensors, communicating wirelessly, dimming lights, and logging data, all at the same time, all in a loop that never stops. But before any of that becomes possible, you need to understand what is inside that chip, how it talks to the board it sits on, and how that board talks to your computer. That is what this entire presentation is about. The label at the bottom right says Independent Study Guide, Embedded Systems Engineering. That means this is designed so that you can follow along, pause, try things on your own machine, and learn at your own pace. Please do that. Do not just watch. Interact with every slide. Let's begin. What to point to? The ATmega 328P chip in the center of the image. The blue and green arrows spreading outward from all sides of the chip, emphasizing the quantity of I/O connections. The Independent Study Guide label. This sets expectations for interactivity. What the audience should do. Check mark action. Open the Arduino IDE on your computer right now. If you don't have it installed yet, go to arduino.cc/n/software. Download the latest version and install it. Keep it open in the background. We will use it later in the session. Now let's zoom out and look at the Arduino Uno as a complete system. You might think of the board as a single object, but engineers see it as four distinct subsystems working together. I want you to look at the image of the Uno in the center. And as I describe each subsystem, I want you to physically locate it on the board in front of you, or on the image on screen. Subsystem 1. The brain. MCU. The large rectangular black chip labeled ATmega 328P near the center bottom of the board. This chip executes every line of your code, in a loop, without an operating system. It is the engine of the entire board. Subsystem 2. The communication bridge. USB. The USB port on the top left of the board. This is the primary highway between your laptop and the microcontroller. When you click Upload in the Arduino IDE, your code travels through this port as data, and power flows back in the other direction. Without this bridge, the board cannot talk to your computer at all. Subsystem 3. Power infrastructure. The barrel jack connector, round hole, and the row of power pins labeled G and 5 volts and 3.3 volts on the bottom left edge. These regulate and distribute safe voltages to every component on the board. We will go much deeper into this in a later slide. Subsystem 4. The sensory system. I/O pins. The two rows of pins along the top and bottom edges. These are the hands and ears of the board. The physical connection points where sensors, LEDs, motors, buttons, and all real-world components plug in. Every project you ever build lives inside these four subsystems. If your project breaks, the fault is always in one of these four areas. Understanding this blueprint is your diagnostic superpower. What to point to? The ATmega 328P chip at the center bottom of the board image. The USB connector on the top left, with the label the communication bridge. The power components, barrel jack, capacitors, voltage regulator, on the left, with the power infrastructure label. the 2 rows of pin headers along the edges. With the sensory system, I/O pins. Label. What the audience should do. Check mark action. If you have a physical Arduino Uno, pick it up now and locate each of the 4 subsystems with your finger. If you are working from a screen only, draw a rough sketch of the board and label the 4 zones. This physical mapping exercise is critical. It prepares you for practical module 1. Let's now zoom all the way in on subsystem 1, the microcontroller unit, or MCU. I want to correct a common misconception right away. When someone says, the Arduino, they usually mean the entire green board. But the actual thinking happens in one specific chip, the ATmega 328P. The board is just the support structure. It provides power conditioning, a USB translator, and convenient pin headers. The chip is the brain doing all the heavy lifting. On the left side of this slide, you see a close-up photo of the ATmega 328P chip with circular arrows around it in the code symbol. Opening curly bracket, closing curly bracket. Those arrows represent the program loop, the single most important concept in embedded programming. Your Arduino program has 2 functions: setup, which runs once at boot, and loop, which runs forever, continuously, until power is removed. There is no task scheduler, no multitasking, no background processes, just one loop. Now look at the 3 text boxes on the right. The Silicon Star. The ATmega 328P is the brain. Everything else on the board supports it. Remember this distinction. The board is not the computer. The chip is. The worker mentality. A laptop has Windows or Mac OS managing hundreds of processes simultaneously. The MCU has nothing like that. It has no operating system. It reads input, processes it, produces output, and goes back to the top of the loop. This makes it extremely predictable and reliable, which is exactly what you need in industrial systems. A motor controller that hesitates because the OS is running a background update is a broken motor controller. Form factor. Look at the chip itself. It has 2 rows of metal legs. This is called a DIP package. Dual inline package, meaning it can be inserted into a socket and removed by hand. On cheaper or more compact boards, the MCU is soldered flat to the board. This is called an SMD package, surface mount device. The difference matters when you want to replace a fried chip. Key term to remember: MCU, microcontroller unit. What to point to: the circular arrows on the chip image, representing the program loop, the symbol, representing code being executed in cycles. Each of the 3 text boxes: Silicon Star, worker mentality, form factor, check mark action. Open the Arduino IDE. Go to File, right pointing arrow, Examples, right pointing arrow 01, Basics, right pointing arrow, Blink. Read the code. Notice the setup function and the loop function. Now mentally trace what happens. The LED turns on, right pointing arrow waits 1 second, right pointing arrow turns off, right pointing arrow waits 1 second, right pointing arrow repeats forever. This is the MCU's worker mentality in code form. Do not upload yet. Just read and understand the loop structure. Subsystem 4, the I/O pins, is where your code meets physical reality. But not all pins are the same. There are 2 completely different types of pins on the Arduino, and confusing them will cause your sensors and components to behave incorrectly. Look at the 2 sides of this slide. The left shows a square wave, sharp edges, perfectly flat tops and bottoms. The right shows a smooth sine wave, flowing curves. These 2 wave shapes represent digital and analog signals respectively. Digital pins. The left column. Digital pins speak in binary. They are either high, 5 volts, or low, 0 volts. There is no middle ground. They are perfect for components that have exactly two states. A button that is pressed or not pressed. An LED that is on or off. A relay that is open or closed. The Arduino Uno has 14 digital pins, numbered 0 through 13. Pin 13 is special. It has a built-in LED connected to it on the board itself, which is why Blink uses pin 13 by default. Now notice the tilde symbol, tilde, next to some pin numbers. 3, 5, 6, 9, 10, 11. These pins support PWM, pulse width modulation. This is a technique where the pin rapidly switches between high and low so fast that the component perceives a value between them. If a pin is at 50% PWM duty cycle, an LED will appear to glow at half brightness. This is how you dim something using what is technically still a binary pin. Analog pins. The right column. The 6 pins labeled A0 through A5 can read a continuous range of voltages, from 0 volts to 5 volts. Internally, they use an ADC, analog to digital converter, which converts the incoming voltage into a number between 0 and 1023. A potentiometer at full turn gives you 1023. At half turn, you get approximately 511. This is how the board understands the physical world. Light intensity, temperature, moisture, pressure, critical distinction. Analog pins read incoming voltage levels. They do not output analog voltages. To produce a smoothly varying output, you use PWM on a digital pin. What to point to? The blue square wave on the left. This is what digital looks like. The green sine wave on the right. This is the analog world. The bullet points under each column. The tilde symbol. Emphasize it appears on specific pins only. Checkmark action 1 on your physical board, or in a diagram. Find pin 13. This is your built-in LED pin. Then find pins 3, 5, 6, 9, 10, and 11. Look for the tilde printed next to the number. These are your PWM-capable pins. Checkmark action 2, in the Arduino IDE. Go to File right-pointing arrow Examples right-pointing arrow 03. Analog right-pointing arrow Analog read serial. Read the code. Observe that it reads from A0 and prints a number between 0 and 1023 to the serial monitor. This is the ADC in action. Now we go deep into Subsystem 3. Power. This is the slide that prevents you from destroying your board, your sensors, and your components. Read every word carefully. Look at the diagram. Power enters the board from two possible sources. The USB port, which provides 5 volts directly, or the VIN barrel jack, which accepts 7 to 12 volts. When you use the barrel jack, the onboard voltage regulator, the 3-legged black component on the left side of the Uno, steps the voltage down to a safe 5 volts for the MCU. The regulator does this by dissipating the excess voltage as heat, which is why boards can feel warm during high load operation. From the voltage regulator, power splits into 3 output channels: 5 volts out, 3.3 volts out, and GND. Now, look at the warning triangles. Warning. Next to the 5 volts and 3.3 volts outputs. These are not decorative. This brings us to the most important box on this slide. The amber warning box on the bottom right. The magic smoke limit. I/O pins can only source or sink between 20 and 40 milliamps of current. Milliamps. That is enough to light a small LED. It is absolutely not enough to power a motor, a solenoid, a relay coil, or any inductive load directly. If you wire a DC motor directly to a digital pin and turn it on, you will fry the internal copper traces inside the chip. The board will appear to work briefly, then fail permanently. Experienced engineers call this releasing the magic smoke. Once it's out, it never goes back in. The critical anchor. GND. Look at the bottom of the diagram where GND forms a complete return loop. Ground is not optional. It is not just a negative terminal. It is the reference point that makes all voltage measurements meaningful. Every component you wire to the Arduino must share a common GND connection with the board. A sensor floating without a ground connection will read garbage data every time. Output rails. The 5 volts and 3.3 volts pins on the power header can source power for external sensors and modules, but never exceed the board's total current budget, approximately 500 milliamperes from USB, or up to 1A from a wall adapter through VIN. What to point to? The green flow diagram. USB, VIN right pointing arrow voltage regulator right pointing arrow 5 volts out, 3.3 volts out GND. The GND feedback arrow completing the loop. Electricity must travel in a loop. The amber warning box. Read it aloud word for word. The warning triangles next to the power outputs. Check mark action. On your physical board, locate the 3 power pins in the power header group. GND, 5 volts, and 3.3 volts. These are your safe power rails for external sensors. Now locate the voltage regulator. The small 3-legged black component near the barrel jack on the edge of the board. Touch it lightly after the board has been running for a few minutes. It will feel warm. That warmth is the excess voltage being dissipated. Warning rule to memorize. Never connect a motor, relay, or solenoid directly to a digital I/O pin. Always use a motor driver IC, such as the L298N, or a transistor as a buffer. Let's now understand how your code actually gets from your laptop into the chip. This is Subsystem 2, the communication bridge, and it involves a translation process that most beginners never think about. Follow the pipeline in the diagram from left to right. Step 1. USB data. Host. Your laptop sends data using the USB protocol. USB is a sophisticated, high-level communication standard designed for general-purpose computers. It handles error correction, device enumeration, power negotiation, and much more. Step 2. The problem. The ATmega 328P chip cannot speak USB. The chip only understands a much simpler protocol called serial communication, sometimes called UART, Universal Asynchronous Receiver Transmitter. Serial communication is just a stream of ones and zeros. Send 1 bit at a time down a single wire. Simple. But USB and serial are incompatible languages. Step 3. The USB to serial translator. E.g., CH340. This is the hidden hero of the board. There is a small chip. On genuine Arduino boards it is an ATmega 16U2. On many affordable clone boards it is a CH340, whose only job is to sit in the middle and translate. It receives USB packets from your computer, extracts the actual code data, and re-sends it as clean serial pulses that the ATmega 328P can read and execute. The 3 boxes at the bottom explain the key insights. The bottleneck. This translation step exists because microcontrollers are designed to be simple and power efficient. Adding a full USB interface to every MCU would make them expensive and complex. So the translation is offloaded to a dedicated chip, the translator. Think of the USB to serial chip as a real-time interpreter at an international conference. It listens to one language and re-speaks it in another. In real time. Hardware note. This is critical for Windows users. If you plug in a clone Arduino board and Windows cannot find it, the USB to serial chip is almost certainly a CH340. You must manually install the CH340 driver from the manufacturer's website on macOS Ventura and later. The CH340 driver is sometimes blocked by security settings and requires manual approval in System Preferences. Right pointing arrow. Privacy and security. Official Arduino boards with the ATmega 16U2 chip do not have this problem. The pipeline diagram. Laptop right pointing arrow, USB signal right pointing arrow, translator chip right pointing arrow, serial signal right pointing arrow, MCU chip. The waveform between the translator and the MCU. Those square pulses are serial data. The three text boxes. Bottleneck. Translator. Hardware note. Checkmark. Action 1. Plug your Arduino board into your computer with a USB cable. Open the Arduino IDE. Go to Tools, right pointing arrow, port. You should see a COM port appear. Windows, e.g., COM3, or a dev TTY, USB serial port. Mac, Linux. If no port appears, your USB to serial chip driver is not installed. This is the most common first-time setup failure. Checkmark. Action 2. Windows only. If no COM port appears, open Device Manager. Search for it in the Windows Start menu. Look under Ports, COM and LPT, or Other Devices. If you see a device with a yellow warning triangle, right-click right pointing arrow, update driver right pointing arrow, search automatically. If that fails, search online for CH340 driver, download, and install manually. This is our first hands-on practical module. Put down your notes and pick up your board. Or pull up a high-resolution image of an Arduino Uno on your second screen. The goal of this module is to translate a 2D diagram into a 3D physical landscape before you ever apply power. Many beginners skip this step. Plug in their board, open a tutorial, and immediately start wiring randomly. They then wonder why nothing works. The professional approach is to know the board before touching it. Let's do that now. Mapping the rails. Look at the diagram on the right side of this slide. The two rows of pins along the top edge are your digital pins, numbered 0 through 13. On the physical board, pin 0 is closest to the USB connector, and pin 13 is furthest on the opposite side. In the bottom right area, you have analog input pins A0 through A5. A0 is closest to the edge. A5 is closest to the power header. Shield compatibility. Notice that both rows of pin headers have a standard spacing of 2.54 mm, 0.1 inches. This standard means that Shield expansion boards, dedicated add-on boards for motor control, Wi-Fi, Ethernet, GSM, LCD displays, and more, can stack directly on top of the Uno, connecting to all pins at once with no wiring required. Advanced interfaces. Now locate the 6-pin cluster in the lower right corner of the board, labeled ICSP in the diagram. ICSP stands for In-Circuit Serial Programming. This header allows advanced users to program the ATmega 328P chip directly, bypassing the USB to serial translator entirely. This is how you would recover a board with a corrupted bootloader, or program a blank chip for the first time. Reset button. Located in the upper left area of the board, the small circular button near the USB port. Pressing it forces the MCU to restart and rerun setup. It does not erase your program. The code is stored in flash memory and survives a reset. The annotated blueprint diagram on the right side of the slide. The Reset button label pointing to the top left area. The pin headers. Digital and analog. Label pointing to the 2 rows of headers. The ICSP cluster. Advanced interface. Label pointing to the 6-pin cluster. Checkmark Action 1. Hold your Arduino Uno with the USB port on your left. Starting from the USB side, count the digital pins along the top edge. 0, 1, 2, 3, 4, up to 13. Say the numbers aloud as you count. Now flip to the other side and find a 0 through a 5. Checkmark Action 2. Using a sticky note or masking tape. Label pin 13 on your board. It's the built-in LED pin. Your most used pin for testing. Label GND and 5 volts on the power header. These 3 locations are where 90% of beginner projects start. Checkmark Action 3. Find the 6-pin ICSP header cluster. Do not connect anything to it. Just know where it is. It will become important if you ever need to restore a board or burn a new bootloader. Practical Module 2 is about verifying that your hardware and software have successfully recognized each other. In engineering, this is called a handshake, a confirmed, two-way acknowledgement that both sides are ready to communicate. Before you upload a single program, you need to confirm 3 things. The pulse, power integrity check. When you plug in the USB cable, watch for a green or orange LED labeled ON or PWR on the board. A steady, solid glow means the board is receiving 5 volts and the power infrastructure is healthy. This LED is connected to the 5 volts rail before the voltage regulator. So if it dims when you connect other components, you are drawing too much current and exceeding the 500 mA USB limit. That is your first warning sign. Look at the left half of the slide. The macro photo of a glowing green LED on a circuit board. That bright, steady light is your pulse check. If it flickers, the USB cable may be damaged. If it doesn't light at all, the board is not receiving power. Addressing the hardware. COM port assignment. Now look at the Arduino IDE screenshot on the right side of the slide. The image shows tools right pointing arrow port with COM1, COM2, COM3, COM4 listed, and a check mark next to COM3. Every time you plug in a new USB device, your operating system assigns it a COM port. Windows, Array, Dev, TTY path, Mac, Linux. The Arduino IDE must be pointed at the correct port. Otherwise it doesn't know which physical device to send the compiled code to. Critical rule. The COM port number can change every time you plug the board into a different USB port on the same computer. Always check tools right pointing arrow port before uploading. Two-way communication. The serial monitor. Once your code is uploaded and running, the serial monitor becomes your most powerful debugging tool. Press Ctrl plus Shift plus M. Or go to Tools right pointing arrow serial monitor. To open it, the MCU can send text back to your computer using serial, println commands in your code. This allows you to print variable values, sensor readings, error messages, and status updates, all in real time. It is the embedded developer's equivalent of console.log. In web development, the glowing green LED macro photo on the left. This is what power integrity looks like. The Arduino IDE screenshot on the right. Walk through tools right pointing arrow port right pointing arrow COM3 selection step by step. The serial monitor option in the tools menu in the screenshot. Checkmark Action 1. Plug in your Arduino board. In the IDE, go to Tools right pointing arrow board right pointing arrow Arduino AVR boards right pointing arrow Arduino Uno. Then go to Tools right pointing arrow port and select the port that appeared when you plugged in the board. Checkmark Action 2. Now upload the blink sketch. File right pointing arrow examples right pointing arrow 01. Basics right pointing arrow blink. Click the right arrow upload button. Watch for the progress bar at the bottom of the IDE. The RX and Texas LEDs on the board should flicker rapidly during upload. After upload completes, pin 13's LEDs should blink once per second. Checkmark action 3. Modify the blink sketch. Change delay 1000 to delay 200. Upload again. The LED should now blink 5 times per second. You have just confirmed full two-way communication between your laptop and the MCU. Practical Module 3 is the most physics-intensive section of this module, and also the most important one for keeping your components alive. We are going to understand how electricity flows through a circuit, why direction matters, and how to calculate the resistor you need before connecting anything. Look at the circuit diagram on the left. This is a simple LED circuit on a breadboard, connected to the Arduino's 5 volts and GND pins. Circuit continuity. Electricity is not a one-way flow. It must travel in a complete loop. Current flows from the 5 volts pin, through the red wire, into the positive rail of the breadboard, through the LED, through the resistor, into the negative rail, through the black wire, and back to the GND pin on the Arduino. If any one of these connections is broken, if even one wire is loose, current cannot flow and nothing happens. This is the most common cause of a circuit not working. It is simply not a complete loop. Polarity matters. LEDs are polarized components. Current can only flow through them in one direction. The long leg is the anode. Plus, current enters here. The short leg is the cathode. Minus, current exits here. If you insert an LED backwards, it will not light up, and it may be damaged. Always identify the legs before wiring. Current limiting buffer. The resistor. An LED connected directly between 5 volts and GND with no resistor will instantly receive full current, exceed its maximum rating, and burn out, sometimes in under a second. A 220 ohms resistor placed in series with the LED limits the flow of electrons to a safe level, typically around 15 to 20 milliamps. Ohm's law. The formula. Look at the teal box at the bottom right. R equals V underscore source minus V underscore forward. This formula tells you the exact resistor value needed for any LED circuit. Let me walk through it. V underscore source is your supply voltage. In our case, 5 volts. V underscore forward is the voltage the LED naturally consumes to produce light. Typically 2.0 volts for red, 3.0 volts for blue-white. I is the desired current. We target 0.02 A, 20 milliamps. Example, for a red LED on 5 volts, R equals 5 minus 2.0. 0.02 equals 3.0 divided by 0.02 equals 150 ohms. Round up to the nearest standard value. Use a 220 ohms resistor. The LED will be slightly dimmer than maximum, but it will last for years. This is the professional approach. The breadboard diagram. Trace the current path with your finger. 5 volts right pointing arrow red wire right pointing arrow breadboard rail right pointing arrow anode right pointing arrow cathode right pointing arrow resistor right pointing arrow GND rail right pointing arrow black wire right pointing arrow GND pin. The LED symbol. Point to the long leg, anode, and short leg, cathode. The resistor symbol in the diagram. The Ohm's law formula box. Write it on the whiteboard if available. Checkmark action 1. Using a breadboard, a 220 ohms resistor, an LED, and 2 jumper wires. Build the circuit shown in the diagram. Connect the red wire to the 5 volts pin on the Arduino and the black wire to GND. The LED should light up immediately. Checkmark action 2. Calculation practice. If you have a blue LED, V_forward approximately equals 3.0 volts, and you are powering from 5 volts at 20 milliamperes. Calculate the required resistor using Ohm's law. Answer: R equals 5 minus 3.0. 0.02 equals 100 ohms. Use a 150 ohms or 220 ohms resistor as the nearest safe option. Checkmark action 3. Flip the LED around. Swap anode and cathode. Observe that it no longer lights up. Flip it back to the correct orientation. This teaches polarity through direct experience. Not all Arduino boards are the same. The platform spans a wide range of form factors, and choosing the wrong board for your application is a genuine engineering mistake. This slide gives you the diagnostic matrix to make the right choice. We are comparing 3 boards side by side. Arduino Nano, embedded, compact. The Nano uses the same ATmega 328P brain as the Uno, but in a dramatically smaller package designed to fit directly into a breadboard. It has 14 digital pins and 8 analog inputs. Actually more analog inputs than the Uno. It has 1 hardware serial port. The use case is, you've built your prototype on an Uno. It works perfectly, and now you need to shrink it into a final product or embed it in a small enclosure. The Nano is your production-ready version of the Uno. Arduino Uno, the prototyping standard. The Uno is the default choice for all learning and prototyping. It has 14 digital pins, 6 analog inputs, and 1 serial port. Its large size, clearly labeled pins, and Shield compatibility make it the most forgiving board for beginners. The DIP packaged MCU can be removed and replaced if you damage it. When in doubt, start with the Uno. Arduino Mega 2560. Complex robotics. The Mega uses an entirely different chip, the ATmega 2560, which has 256 kilobytes of flash memory, 8 times more than the Uno's 32 kilobytes. It has 54 digital pins, 16 analog inputs, and 4 hardware serial ports. This is the board for projects where you are simultaneously managing multiple serial devices. A GPS module, a Bluetooth radio, an LCD screen, a motor driver, and environmental sensors all at the same time. Each serial device gets its own dedicated hardware port, eliminating interference. Rule of thumb: learning or first prototype right-pointing arrow Uno. Miniaturizing a working design right-pointing arrow Nano. Managing many peripherals simultaneously right-pointing arrow Mega 2560. Each board photo at the top. Compare physical sizes visually. The comparison table rows. I/O counts. Brain chip. Serial ports. Use case. Highlight the Mega's 256 kilobytes memory versus Uno's 32 kilobytes, 8x more. Highlight the Mega's 4 serial ports versus Uno's 1. Checkmark action. Think about your current or planned project and answer these 3 questions. 1. How many sensors modules will run simultaneously? 2. Will the final device need to be small? 3. Do you need more than 6 analog inputs? Use your answers to select the appropriate board from the matrix. Write your choice down with 1 sentence justifying it. This slide moves us from the beginner to intermediate zone into serious architectural thinking. The most important hardware decision in embedded engineering, beyond which board to use, is whether your application needs an 8-bit or a 32-bit processor. The visual on this slide says it perfectly. A single gear versus a full multi-cylinder engine. The 8-bit tractor. AVR. Boards like the Uno, Mega, and Nano use AVR 8-bit processors running at 16 MHz. 8-bit means the processor handles numbers in chunks of 8 bits at a time. A maximum value of 255 per clock cycle. Anything larger, a 16-bit number, a floating point decimal, a large array, must be broken into multiple steps and processed sequentially. This makes complex math slow. However, 8-bit AVR chips are extremely reliable, have been in production for decades, have vast documentation and library support, and consume very little power. For simple automation, sensor reading, LED control, and relay switching, they are perfect. A tractor doesn't need a V8 engine. It needs to plow reliably for 10,000 hours. The 32-bit sports car. ARM Cortex. Modern Arduino boards like the Giga R1 and the Portenta series use 32-bit ARM Cortex processors, running at up to 480 MHz. 32-bit means they can process numbers up to 4,294,967,295 in a single clock cycle, over 16 million times larger than the 8-bit maximum. At 480 MHz, they execute roughly 30 times more operations per second than the Uno. These chips handle floating point math natively, support real-time operating systems, RTOS, can run multiple threads, and have dedicated hardware accelerators for audio and signal processing. Why it matters. 32-bit architecture is not optional for certain application classes. High-resolution display rendering. Driving a color TFT screen with smooth animations requires processing millions of pixels per second. Audio processing, sampling, filtering, and compressing audio in real time demands floating point operations at high speed. Machine learning at the edge. Running a neural network model on device. TinyML. To recognize a sound, a gesture, or an anomaly requires the raw computational power of a 32-bit core. As you advance into industrial integration, you will encounter both. Start mastering the 8-bit to understand the fundamentals. Then migrate to 32-bit when the application demands it. The single gear icon labeled 8-bit AVR, 16 MHz. Quote, simple, single cylinder power. The multi-cylinder engine labeled 32-bit ARM Cortex, 480 MHz. Quote, complex, high performance. The 3 text boxes at the bottom. Read each label aloud. 8-bit tractor, 32-bit sports car. Why it matters. What the audience should do. Check mark action. In the Arduino IDE, go to Tools Right Pointing Arrow Board Right Pointing Arrow Boards Manager. Search for Arduino SAMD boards. This is the 32-bit ARM board family. Do not install it yet. Just observe that the IDE supports both 8-bit and 32-bit families through the same interface. The programming language, C, C++, is identical, only the underlying hardware changes. This is one of the most important safety slides in the entire presentation. If you internalize one hardware rule today, let it be this. Before connecting any sensor or module to any microcontroller, verify that they operate at the same logic voltage level. Failing to do this will silently destroy your sensors. The damage is instant and permanent. The legacy standard, 5 volts. Older AVR-based boards like the Uno and Mega operate at 5 volts logic. Their I/O pins output 5 volts for a logical high. They can also safely receive anything above approximately 3 volts as a high signal. This makes them compatible with each other, but dangerously incompatible with modern sensors. The modern standard, 3.3 volts. Modern wireless chips like the ESP32, most ARM Cortex microcontrollers, virtually all modern environmental sensors, temperature, humidity, air quality, accelerometers, and all GPS modules operate at 3.3 volts logic. They output 3.3 volts for high, and they are engineered to receive a maximum of 3.3 volts on their input pins. Their internal transistors are microscopic and fragile. The risk. Look at the danger zone diagram on the right. The top scenario shows a 5 volts signal driving directly into a 3.3 volts sensor pin. The graphic shows the signal exploding on impact. Labeled permanent damage. This is not an exaggeration. The 5 volts signal physically overdrives the 3.3 volts input transistor, melting the microscopic copper traces inside the sensor chip. The chip dies. There is no recovery. This failure is especially frustrating because it is often invisible. The sensor might appear to work briefly before the damage propagates. Students frequently conclude the sensor must be defective and order a replacement, only to destroy it immediately again. The professional solution. Logic level converter. Look at the bottom safe diagram. A logic level shifter is inserted between the 5 volts output of the UNO and the 3.3 volts input of the sensor. This small module, typically a bidirectional BSS 138 based converter, available for under $1, steps the 5 volts signal down to 3.3 volts in real time, without losing any data speed. Place one on every mixed voltage connection in your circuit. This is standard professional practice. The 4 text boxes on the left. Legacy standard. Modern standard. The risk. The professional solution. The danger zone. Top diagram. The explosion graphic representing permanent damage. The safe bottom diagram. The logic level converter block cleanly translating 5 volts right pointing arrow 3.3 volts. Checkmark action 1. Look up the datasheet for any sensor you own or plan to use. Search. Sensor name. Datasheet. Find the section labeled Absolute Maximum Ratings or Operating Voltage. If the maximum voltage is listed as 3.3 volts or 3.6 volts, you must use a logic level converter when interfacing with a 5 volts Arduino. Checkmark action 2. Search online for BSS 138 logic level converter or TXBO 108 logic level shifter. Add one to your component kit. They cost less than a coffee and will save you from destroying $10 to $50 sensors. We now cross into the territory that separates hobbyist projects from industrial deployments. Everything we have discussed so far works cleanly on a desk, in a factory, warehouse, or a robotic platform. New threats appear that will crash, corrupt, or physically destroy your microcontroller. This slide is about those threats and the engineering solutions. Look at the oscilloscope trace in the upper left. That chaotic, spiky waveform is what a power line looks like in an industrial environment. Every time a motor starts, every time a relay clicks, every time a fluorescent light flickers, it sends an electrical shockwave through the power lines. This is called electrical noise. Threat 1. Electrical noise. The MCU's power pin is expecting a clean, steady 5 volts. If that voltage dips below approximately 4.5 volts for even a microsecond, the chip's internal logic can misread it as a power-off event and trigger a spontaneous reset. The board restarts. Your code jumps back to setup, and whatever the device was doing, controlling a motor, recording data, holding a valve open, suddenly stops. In an industrial context, this can be catastrophic. Defense 1. Decoupling capacitors. The solution is to place small capacitors, typically 100 nanofarads ceramic, directly adjacent to the MCU's power pins. These act as tiny local batteries. They store a small charge and release it instantly when the main voltage dips. Bridging the gap. The lower oscilloscope trace in the diagram shows the same noisy line after a decoupling capacitor. It becomes a flat, stable signal. The UNO already has these capacitors built in near the MCU. Thread 2. Back EMF. Kickback. When you cut power to a motor or a relay coil, the collapsing magnetic field inside generates a brief but extremely high voltage spike, sometimes 50 to 100 volts, that fires backwards through the wiring into your circuit. This is called back EMF. Electromotive force. This spike is strong enough to destroy the output transistors in your motor driver or even the MCU itself. Defense 2. Flyback diodes and optoisolators. In professional circuits, a flyback diode, also called a freewheeling diode, is placed in reverse parallel across every motor or relay coil. When the spike appears, the diode provides a safe path for the current to circulate and dissipate harmlessly. For complete isolation, optoisolators are used. They translate logic signals into light and back, ensuring that no electrical connection exists between the dirty motor power domain and the clean logic power domain of the MCU. The upper oscilloscope trace. Chaotic spikes. Label. Electrical noise and back EMF right pointing arrow erratic reset. The capacitor symbol in the lower diagram. Label. Stabilized logic power. The lower oscilloscope trace. Smooth and flat after the capacitor. The 4 text boxes on the right. Threat of noise. Local batteries. Kickback threat. The shield. Checkmark action. Search for Flyback Diode Tutorial Arduino Relay on YouTube or Google. Watch the circuit diagram. Note how the diode is placed across the relay coil in reverse orientation. This is a mandatory component in any circuit where you switch a relay, solenoid, or motor using the Arduino. Add 1N4007 diodes to your component kit. This slide describes the most common, most confusing, and most frustrating hardware conflict that Arduino beginners encounter. You will encounter it. When you do, this slide will save you hours of debugging. The hardwired highway. Digital pins 0 and 1 are not ordinary pins. They are labeled RX, receive, pin 0, and TX, transmit, pin 1, on the board for a reason. These 2 pins are physically, electrically hardwired to the USB to serial translator chip, the same CH340 or 80MB16U2 we discussed in slide 6. This connection is permanent and exists whether or not you use those pins in your code. The traffic jam. Imagine you want to connect a GPS module that communicates via serial. Beginner instinct says, I'll use the TX and RX pins. They're serial pins. So you wire the GPS module to pins 0 and 1. Now you try to upload new code. Your computer sends the compiled code through USB, which arrives at the USB to serial chip, which tries to push it through pins 0 and 1. But the GPS module is also trying to send its location data through pins 0 and 1 at the exact same moment. 2 signals collide on the same wire simultaneously. Look at the diagram. 2 arrows. PC uploading code and GPS module data, crashing into each other with the label collision in the center. The result. The IDE shows you a cryptic error. Programmer not responding, or STK500 sync error. Beginners spend hours checking cable connections, reinstalling drivers, and reinstalling the IDE. The actual fix takes 30 seconds. The workarounds. Short-term fix. Before every upload, physically unplug the component from pins 0 and 1. After the upload completes and the code is running, plug the component back in. Simple but tedious. Professional fix. Never use pins 0 and 1 for external components. Instead, use the software serial library to create a virtual serial port on any other two digital pins. For example, software serial GPS serial 4, 5 creates a serial port on digital pins 4 and 5. Your GPS module plugs into those pins instead, and pins 0 and 1 remain reserved for the USB connection. The board diagram in the center. Point to pins 0, RX, and 1, TX. At the bottom of the digital pin row, the two colored arrows converging. Blue PC uploading code from above. Green GPS module data from below. Crashing at the collision label. The four text boxes. Hardwired highway. Traffic jam. The result. The workaround. What the audience should do. Checkmark action 1. In the Arduino IDE. Go to File right pointing arrow examples right pointing arrow software serial right pointing arrow software serial example. Read the code. Notice the line software serial my serial 10, 11. This creates a virtual serial port on pins 10, RX, and 11, TX. This is the correct way to add a serial device without blocking the upload port. Checkmark rule to memorize. Pins 0 and 1 are reserved for USB communication. Never connect an external component to them permanently. We have reached the final slide. The independent verification checkpoint. This is your self-assessment. Close your notes. Do not look back at the previous slides. Answer these questions and complete these exercises from memory and from first principles. Core diagnostic questions. Left column. Question 1. What is the specific architectural limitation of an 8-bit MCU compared to a 32-bit ARM chip? Think about what 8-bit means in terms of data chunk size and maximum per cycle value. Think about what applications require 32-bit computation. Question 2. Why must the GND path always be established before supplying power? Think about circuit continuity. What happens to voltage measurement without a reference point? What happens to current flow without a return path? Question 3. What happens when a 5 volts signal is pushed directly into a 3.3 volts rated sensor pin? Think about the danger zone diagram from slide 12. What happens to the microscopic input transistors? Is the damage recoverable? Question 4. Why do uploads fail when components are wired to pins 0, RX, and 1, TX? Think about the hardwired highway. What two signals collide? What does the IDE error message look like? Applied hardware exercises. Right column. Exercise 1. Tabular analysis. Create a comparison table of the Arduino Uno R3, Mega 2560, and Nano Every. Look up the Nano Every specifications. It uses a newer ATmega 4809 chip. Your table must include columns for MCU type, clock speed, flash memory, SRAM, and number of hardware serial ports. Exercise 2. Diagnostic flowcharting. Map a 5-step decision tree flowchart for diagnosing a board not detected COM port error. Your flowchart should start at board plugged in and branch based on: is the PWR LED lit? Does Device Manager show the board? Is the correct port selected in the IDE? Is the correct board type selected? Each branch should end in a specific actionable step. Exercise 3. Circuit mapping. On paper, draw a complete schematic of a grounded LED circuit driven by digital pin 13. Label the MCU pin, the current direction, The resistor value. Calculated using Ohm's law. Assuming a red LED at 5 volts and 20 milliamperes. The LED with correct anode-cathode orientation. And the GND return path. Your drawing must show every connection in the complete loop. When you have completed all 3 exercises, share your results with a peer for cross-verification. Peer review catches errors that self-review misses. Left column. Read each question aloud, pausing for the audience to think. Right column. Read each exercise aloud and clarify any ambiguous instructions. Emphasize the phrase independent verification. The goal is to confirm mastery without looking at notes. What the audience should do. Checkmark Action 1. Set a 20-minute timer. Write answers to all 4 core diagnostic questions in your own words. Incomplete sentences. Do not use one-word answers. Checkmark Action 2. Complete at least one of the 3 applied hardware exercises in full detail before the next session. Checkmark Ongoing Challenge. Build the LED circuit from exercise 3 on your breadboard. Then modify it. Write an Arduino sketch that slowly brightens and dims the LED using PWM on pin 9. Use analog write 9 value, where value goes from 0 to 255. This combines Ohm's law circuit design with PWM software control. And it demonstrates everything covered in this module working together.